right, lesson 13b, exponential and logarithmic equations and inequalities. So we start out here with some quadratic type exponential equations. And so we want to solve this and then support the answer graphically. So notice that on example 9, it has e to the 2x minus 3e to the x minus 4 equals 0. Well, remember, what would make us multiply in our exponent? That would be if we had a power to a power. So we could rewrite e to the 2x as e to the x squared minus 3e to the x minus 4 equals 0. In this case, we're going to use some substitution. We're going to let some letter, we're going to pick u, and we're going to let that equal our e to the x. So if I substitute that in, I'm going to get u squared minus 3u minus 4 is equal to 0. And so this, we can just X box. We needed to multiply to negative 4, combine to negative 3, so we know it's negative 4 and 1. So we get u minus 4 and u plus 1 equals 0. And we can go ahead and just solve for u. So set them each equal to 0 and solve. So I'm going to add the 4 and I'm going to subtract the 1. But remember, we're not trying to solve for u, we're actually trying to solve for x, because that's our variable in the original problem. So now we're going to substitute back. So remember, u was just e to the x. So e to the x equals 4, and e to the x equals negative 1. And then I'm stuck in exponential form, so I'm going to change it to log form. So I end up with log base, well, let me write this out first. So my base is e. b to the y is my x, and my x is 4. So I have log base e of x equals y, which y is our x. All right, and so I know then that x is equal to log base e is just the natural log of 4. Can do the same thing with the other side. So I know that my base is e, b to the y, so my y is x, b to the y equals x, and so my x is negative 1. So I'm going to change it to log form, so log base b of x equals y, and so x is equal to the natural log of negative 1. Now, anytime when we leave it in natural log, we need to make sure we think about it, or any log. So remember that this number right here has to be greater than 0. So since that first one there, the natural log of negative 1, the negative 1 is not greater than 0. It is an extraneous solution, which means it's not really an answer. So therefore, we only end up with that one answer. And I'm going to just box it this one time. So this is what they call that extraneous solution. And a lot of times when I do it, I just write the word check at the bottom. That reminds me I need to check it or that I did check it. All right, so example 10 is really similar. Difference with example 10 is now it's a fraction. Well, we know how to get rid of fractions. We're just going to multiply both sides by 2. So we have e to the x minus e to the negative x equals 16. And so I could move that 16 over, so e to the x minus e to the negative x minus 16 equals 0. Well, if I could make that an e to the x squared again, then I could use substitution like I did on the previous one. So what will happen if I multiply to get e to the x squared right here in this first term? I just need to multiply it times itself. So I'm going to multiply everything here by e to the x. So when I do that, I get e to the, remember when you multiply, you keep the base, add the exponents, x plus x is 2x, minus, add the exponents again here, so e to the 0, minus 16e to the x equals 0. So this first one is my e to the x squared, minus e to the 0 is 1, minus 16 e to the x equals 0. Well, now it's just written out of order. So I'm just going to switch these so it's in descending order of the exponent. So I have my e to the x squared minus 16 e to the x minus 1 equals 0. So then using substitution, I'm going to let u equal e to the x. So I have u squared minus 16u minus 1 equals 0. Well, I can try to Xbox that, but it's not going to work. So I wrote way too big on this problem at the beginning. I apologize. Xbox isn't going to work, so I'm going to have to use my quadratic formula. All right, so I'm just going to borrow the space on this other problem here. I'm going to erase it so that I can use it to be able to write and show my work. I'm sorry about writing too big, but it is what it is. All right, so I know that my A is going to be 1, my B is negative 16, and my C is negative 1. So remember your quadratic formula. This is x equals, in this case it's u equals negative b plus or minus the square root b squared minus 4ac all over 2a. So I'm going to go in here and plug stuff in. So it's negative 16, a, c to a. And I'm just going to work on simplifying that. So u equals 16 plus or minus the square root of, and so that gives me 260 over 2. And so now I'm going to go and I'm going to have to break down that 260. So I know that's 26 and 10, 2 and 13, 2 and 5. So I have a group of 2's, and I'm going to leave the 13 and the 5 underneath. So I end up with u is equal to 16 plus or minus 2 square root of 65 all over 2, which reduces, so I end up, whoops, my 16, my 2, and my 2 are all divisible by 2, so it gives me 8 plus or minus the square root of 65. So I know that u is equal to 8 minus the square root of 65, and u is equal to 8 plus the square root of 65. But remember, we're not solving for u, we're solving for x, and we said u was equal to e to the x. So e to the x equals 8 minus square root of 65, and e to the x equals 8 plus the square root of 65. So when I change this to log form, I get log base e of 8 minus square root of 65 equals x. We know that log base e is a natural log of 8 minus square root of 65 is equal to x. But remember, check it. 8 minus the square root of 65 is going to be negative because square root of 64 is 8, so the square root of 65 is bigger. So this is going to be negative, so that is also an extraneous solution. So I'm going to work out this other side. So log base e of 8 plus square root of 65 equals x. And so we get x is equal to the natural log of 8 plus square root of 65. Now I'm taking 8 and I'm adding a little bit more than 8, so I'm going to end up with 16 point something, which works. So this is our solution. And I know we're not supposed to box, but I've got a lot going on there. So just be careful, make sure you wrote small. All right, example 11. They're just quadratic type logarithmic equations. And so notice here we have a lot of logs going on. Well, I have 2 of them on that left side, so I can actually combine those logs. So I can combine these 2 because they're being added. I can combine them by multiplication. So I'm going to take the 3x minus 2 times the x minus 1, the log of both of those, equals, and I'm going to go ahead and move that 2 as its exponent. because I'm already seeing I have a log on both sides that have the same base. So I'm going to work out this piece inside here. So I have the natural log of 3x squared minus 3x minus 2x, so minus 5x plus 2 equals that natural log of x squared. Now because I have a natural log equal to a natural log, those will cancel. And so we know that 3x squared minus 5x plus 2 equals x squared. And now we can just solve that. So let's subtract the x squared over. So 2x squared minus 5x plus 2 equals 0. And we can x box this. So 2 times 2. So I need two things that multiply to 4 and combine to the negative 5. So negative 4, negative 1. Just be careful. This is a 2x squared. So remember, when you factor and it's got a number in front, you put that number in your factors. So we have 2x minus 4 and 2x minus 1. And then check and see if either one of these will reduce more. Well, the first one does. They're both divisible by 2. So we get x minus 2 times 2x minus 1 equals 0 when we factor it out. We can set them each equal to 0 now and solve. So x minus 2 equals 0. 2x minus 1 equals 0. Add the 2. Add the 1. So 2x equals 1 and divide by 2. Now remember, if you have log in the original problem, you have to check your answer, okay? Because this number here can be positive or negative. But when I plug it in up here, and what we're taking the log of, it has to be positive. So, sorry about that. Let me erase those circles that I just drew. And let's check it. So let's check the 2. So when I do this first one, 3 times 2 minus 2, 6 minus 2 is 4. That's good. It worked in the first one. When I plug in 2 into the second one, 2 minus 1 is 1. That's good. Both of those are positive, so 2 is definitely an answer. And I know we normally don't box, but we're just going to make do with this right now. Now I'm going to check the 1/2. So I'm going to erase what I wrote up here. When I go and check the 1/2, I get 3 times 1/2 minus 2. Well, 3 times 1/2 is 1.5. Minus 2 is a negative 0.5. I can't have a negative there, so therefore this x equals 1/2 is that extraneous solution. Okay, so make sure you check. Let's try example 12. So example 12, I notice I have two logs on the same side. I have log plus a log, so I know I can combine them by multiplying. So log base 3 of x times x minus 8 equals a 2. We'll go ahead and distribute that x. So log base 3 of x squared minus 8x equals 2. Now this time I just have a single log, so therefore I can change it to exponential. So I know that my base is 3, my x is the x squared minus 8x, and my y is 2. So b to the y equals x. And then just solve this. So we have 9 equals x squared minus 8x. Move the 9 over. So 0 equals x squared minus 8x minus 9. That's just factoring using that x box. They're going to multiply to negative 9 and combine to negative 8. So negative 9 and positive 1. So we get x minus 9 times x plus 1. And then set them each equal to 0 and solve. But make sure, because we have a logarithm in the original problem, you have to check those answers. So check the first one, check the 9. You just get log base 3 of 9. That works. 9 minus 8 is 1. That's positive, so it works. So we know that 9 is a solution. Then check the -1. When you plug -1 right there, it does not work. You cannot take log base 3 of -1. So that is that extraneous solution. All right, example 13 says you have deposited $1,000 in an account that pays 6.5% interest compounded continuously. You can find the balance in your account using this formula. AFT is equal to 1,000 times E raised to the 0.065T. Use this formula to find the time required for your balance in the account to double. So y'all have seen this one pretty recently. So double the amount. If we're starting out with 1,000, then ending amount would be 2,000. And if I want to solve for t, I got to get that exponential part by itself, so I'm going to divide by 1,000. So we get 2 is equal to e raised to the 0.065t. And I'm in exponential form, so I can change it to log form. So I know my base is e to the y is 0.065t, and my x is 2. So log base b of x equals y. We know that log base e is the same as the natural log. And then we can divide by the 0.065 so that we can solve for t. And so we get t is approximately 10.664 years. B says to find the inverse and explain the meaning of the inverse function and context. All right, so to find the inverse, we know our equation is y equals 1,000 e to the 0.065t. So we're going to switch the, well, let me write it out. So to find the inverse, remember we switched the x and y. I'm going to change the t to an x, though. That way it makes sense to us. So I'm going to divide by the 1,000. And now I'm stuck in exponential form, so I'm going to change to log form. So I know my base is e, my y is the 0.065y. And my b to the y, and my x is the x over 1,000. So I have log base b of x equals y. So that means the natural log of x over 1,000 equals 0.065. Now, I'm going to rewrite that x over 1,000 because, sorry, I forgot my y. So, because I know I'm about to divide and I don't like fractions within fractions, this, remember, is like a 1x over 1,000, and 1 over 1,000 is 0.001 x. It doesn't matter, though. You could have left it the other way. And so we know that the inverse is equal to the natural log of 0.001. I'm going to change that back to t now, over 0.065. And so what that gives us, it's going to give us the year when the balance in the account is known. So because before we were finding the balance, when we switched the x and y, now we're finding the time. So this is going to be, so the inverse is the time when the balance in the account is known. All right, C says to graph the inverse with the scale on the x-axis from 0 to 3,000 and the y-axis is 0 to 20. All right, well, I know at the top that the ending amount from A, I know it's going to have the point, the original function, let me do this, A of t would have the point 10.7 approximately. This is from part A to get 2,000. So remember the inverse, we're going to switch them. So it's going to have the 2,000 and 10.7. Well, I can't get my thing to draw for me here. There we go. Let's see. I could find 0 using the original one. The original equation, if I plug in 0, I would get 1,000. So that means that I would have the order pair 1,000, 0. And so I know my graph is going to do something like this, because we know it's a log, so it's going to look something like that. I could also, here at D, it says to find the inverse of the 1,500, explain the meaning and context of the scenario. All right, so when my inverse is 1,500, the inverse of 1,500 is going to equal the natural log of the 0.001 times 1,500 over the 0.065. And so I just calculate that and I get 6.238. And so remember 1,500 is the ending amount. So this is going to be the time. So this is the years. And so there's another ordered pair if I wanted to use it. To go back up and just check my table. So at 1,500 I should be at about 6.2. That doesn't look like I'm too far off on that. All right, example 14. Approximating solutions. It says equations that involve combinations of exponential and logarithmic functions and or algebraic functions can be difficult to solve by algebraic methods. Let's take advantage of technology with these examples. So in example 14, it wants us to complete the table to find the interval containing the solution of the equation. Use a graphing utility to graph both sides of the equation to estimate the solution. Round your answer to 3 decimal places. All right, so I'm going to type, first it wants us to just type the e to the 2x in our calculator. So we're going to go to y equals, and y1, let's type in e to the 2x. But then it wants me to look at these specific x values. So I have two choices. I can make a window where it'll show me them by point ones, or I can go to second calc value and type in these numbers. I'm just going to change my table because sometimes changing the table isn't bad. So if we go to second window, first thing you'll see is table start. Well, I want to start at 1.8. And then I'll see my change in table, and I want to change that to 0.1. So then I go to my second graph to look at my table, and I can see 1.8 is 36 point, I'm just going to round to 1 decimal place here, 36.6. 1.9 is 44.7. 2.0 is 54.6. 2.1 is 66.9. And 2.2 is 81.5. All right. Now I want to know when is it equal to 60. So I can see that it is going to equal 60 somewhere between these two numbers. So I know it's on the interval from 2 to 2.1. Now if I want to find out exactly where it is, we're just going to graph it. So I'm going to say e to the 2x for my y1, which we already had. And in y2, I'm going to put 60, and I'm going to go find their intersection. So you're going to have to mess with your window of your calculator a little bit there to be able to see it. And so when I find the intersection, I find that it's at 2.047 because it said to round the answer to 3 decimal places, and which is between 2 and 2.1. All right, so for B, we're going to do the same thing. So we're going to type in our y equals. We're going to go 2 log base 3 of 0.5x. And because I do that, now I changed my window earlier. So either I need to change my window back or I needed to clear my calculator. So nothing else. We can go to second window. I want to, my table start, I'm going to be lazy. I'm going to go ahead and let it start at 8. And in the change in table, I want them by whole numbers. So I'm going to set that to 1. All right, so then go to your table. You'll see that 8 is like 2.5. 9 is 2.7. 10 is 2.9. 11 is 3.1. And 12 is 3.3. And I'm looking for where it's going to equal 3. So I can see that it's going to be 3 in between 10 and 11. So it's going to be on the interval from 10 to 11. So again, in y1, you already have your 2 log base 3 of 0.5x. y2, put the 3. Probably have to adjust your window again. So find your intersection, and you should see that x is equal to 10.392, which is between 10 and 11. Okay, example 15 says to solve algebraically and check your results on a graphing utility. So first thing is, this is similar to example 10. So let's do kind of the same thing we did there. So let's go ahead and let's get rid of the fraction. And then I'm going to go ahead and get everything on the same side. Now, just like before, I want to make this first term here be a 3 to the x squared, because I see I have a 3 to the x thing going on here, okay? So I just need to multiply, I need to multiply everything by 3 to the x. So multiply every single term here by 3 to the x. And so this is going to give me that 3 to the 2x minus, this is going to give me 3 to the 0, because remember when you multiply, you add the exponents. And then this is going to be minus 10 times 3 to the x equals 0. All right, so this is 3 to the x squared minus 1 minus 10 times 3 to the x equals 0. So I'm going to put them in descending order of the exponent. So I have my 3 to the x squared, and then we'll put my minus 10 times 3 to the x, because that's 3 to the x to the first, minus 1 equals 0. Now I can see both of these terms have a 3 to the x, so let's use substitution. So we're going to let u equal 3 to the x. So when I do that, I have u squared minus 10u minus 1 equals 0, which is not factorable. So I'm going to switch over to the quadratic formula. So now my a is 1, my b is negative 10, and my c is negative 1. So u equals negative b plus or minus the square root, b squared minus 4ac all over 2a. And then let's fill in our blanks here. So I get 10 plus or minus the square root of, so negative 10 squared is 100. Negative 4 times 1 times negative 1 is plus 4, so 104 over 2. I'll come over here to the side. I'm going to factor out that 104. That's what? 52 times 2. There's 26 times 2. So 13 times 2 times 2 times 2. So this is 10 plus or minus 2 square root of 2 times 13, so 26, all over 2. So everything here on the outside is reducible by 2, so I get 5 plus or minus square root of 26. But remember, we use substitution, so we're going to substitute back. So I'm going to come up here to the top. So we had that u was equal to 5 plus or minus the square root of 26. And we know u is that e to the x. So I know my base is e. B to the y, so my y is the x, and my x is 5 plus or minus square root of 26. So actually I'm going to write this out 2 different times. So I'm going to have e to the x equals 5 plus the square root of 26. And I have e to the x equals 5 minus the square root of 26. So I'm going to get log base e of our x. So this one is the 5 plus square root of 26 equals our y. So x equals log base e is a natural log of 5 plus square root of 26. I'm adding from the 5, so I know it's getting, square root of 26 is a positive number, so I know it's getting bigger, so that's an answer. I'm going to do the same thing here. So I have log base e of my x equals the y. And so x equals a natural log of 5 minus square root of 26. Well, square root of 26 is 5 point something, because the square root of 25 is 5, so this is a little bit more. So if I take 5 minus 5 point something, that's going to be negative. So this solution does not work. That's that extraneous solution. All right, and then it says to check it graphically. So if I use my y1, y2, so let's see. I'm going to put the left side here in y1. I'm going to put the right side here in y2. And so I graph it and look at it. It's going to look something like this. And I go find that intersection. And I'll find that intersection is 2.105, 5. If I plug this into my calculator, I'll get approximately 2.105. And so I solved it and I checked it.